Hello everybody, I'm Dr. Sreedevi, Assistant Professor, IARE, Hyderabad. Today in this session of graph theory, we are going to discuss the topic of covering. Already we have discussed what is matching and now we are going to discuss what is covering. From the definition of graphs, we know that if we are given an edge with two endpoints, with its end vertices, then we are saying that that edge is incident with those vertices. Suppose if we E equal to UV, then we are saying that E is incident with the vertices U and V. Also that vertices U and V, U is said to be incident with edge E and V is said to be incident with the edge E. With the same fact can we say that still now we were using that it was incident with. Now we can say that the edge E covers the vertices U and V. Also the vertices U and V covers the edge E. Okay, now we are going to give the formal definition of what is covered. Before going to the formal definitions, now what we will discuss here is we will be giving 2-3 graph invariants. What is the graph invariance? The property which depends on the conductivity. That is what is called graph invariance. Graphical properties which depends on some quantities. The minimum number of vertices that is required to the quantities that we are going to find here is the minimum number of vertices that which required to cover all the edges, and also the minimum number of edges required to cover all the vertices of a graph. And with this we get another two quantities which are called the maximum number of non-adjacent vertices and maximum number of non-adjacent edges. And we will see what are these things and all, and we will see some of the properties regarding these things. These four numbers associated with any graph satisfy several relations and also suggest the study of several vertices and edges which are critical for covering purposes. This minimum number of vertices and minimum number of edges required to cover the graph, also the maximum number of independent vertices and edges. The criteria for the existence of graph with these numbers are established in terms of covering properties of a graph. Okay, we are going to learn about the graph G and set of edges. G is if G is a collection of some subsets of edges of G, then G is said to cover G, that is small g is said to cover the graph G if every vertex in G is incident with at least one edge in G. That is, if we are taking a subset of edges of G. G means this graph capital G and we are naming it to be small g. That subsets of edges are named to be small g. Then the G is said to cover this G if every vertex of this, that is every vertex of this graph has at least one end in this G. That is, this small g is incident with all vertices of G. That we will see the different definitions of that. That a set of edges that cover G is said to be an edge covering or simply covering of G. Now that if for every graph is a subgraph of itself, that we know. Similarly, this G trivially its own covering. Why? Because it goes through every vertex is there in that graph. So it's trivially its own covering. Then spanning trees. What is spanning tree? The tree which contains all the vertices of a spanning subgraph means subgraph which contains all the vertices of the graph. And spanning tree of a graph means contains, it is a subgraph which contains, which is also a tree and contains all the vertices. So every vertex of the graph is incident with at least one edge on that graph. So it is a covering. And if we have seen that every graph doesn't have any Hamiltonian circuit center, but if a Hamiltonian circuit exists, then it also is a covering. Why? Because consider this Hamiltonian circuit graph with having a Hamiltonian circuit. If we are having this vertex, we can go through this vertex from here, like this. We go through all the vertices. So that every vertex is incident with at least one edge in that. It is it's an endpoint of at least one edge. So this is also a covering. Hamiltonian circuit of a graph, if it exists, is also a covering. And can now consider this graph. These edges, if I am taking these two edges, what is the endpoints? The four endpoints, four vertices are also covered. So it is also a covering. Now we'll see different types of covering. And edge, we have seen this maximal subgraphs and all. Same time, here we are going to be minimal covering. Minimum number of edges or minimum number of vertices that are required to cover the graph. Those terminologies we are going to discuss here. An edge covering from which no edge can be removed without destroying its ability to cover the graph is said to be a minimal covering. That is, this minimal covering means there exists no other covering which is an edge covering. Minimal edge covering. Okay, consider the graph with two different minimal coverings. Now, if you have the same graph, you can see that it is both 1 and 2 are same graphs. Same number of edges, same number of vertices, they are same thing. But the first one, you can see that I have drawn 6. Now consider these graphs 1 and 2. Here it is the same graph. The number of vertices, here we can see that some lines, edges are drawn in blurred lines, and here also some blurred lines. So here we can see that there are 6 lines, and we can see that with these 6 lines we can cover all the vertices. Is it so that here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices are here, and with these 6 edges, because look at this, first, second, third, fourth and fifth. Sorry, 6. With these 6 edges, I can cover all the vertices. And considering this, another 8, 1, 2, 3, 4, 5, 6, 7, 8. With another 8 edges, I can cover this. Both the coverings are minimal in sense. Why? Because if I am removing any edge, if I am removing this edge, will it cover the graph? No. And if I am removing any edge from here, suppose I am taking off this edge, will it cover? No. So it's a minimal in sense itself. Okay. So a graph can have different minimal coverings. Observations on edge covering. Okay. A covering of a graph exists if and only if graph has no isolated vertex. Suppose if I am having one vertex here in this graph associated with this graph 2. But does this do any edge is connected with this isolated vertex? No. And according to the definition, what is the condition of edge covering? Every vertex should be at least one endpoint of the set of edges that we are taking, and we cannot find an edge falling on this vertex. So, for considering the edge covering of a graph, we should have a graph. Graph should not have any isolated vertex, or the graph should be a connected graph. And so, it should not have no isolated vertex. And the covering of a graph of order n, a covering of a graph of order n has at least n by 2 edges. This integer modulo not less than x. Okay, integer modulo not less than n by 2. Every pendant edge on a graph should include in every vertex covering. Every pendant edge in a graph should be could be included in every edge covering of the graph. Why? Considering this graph, this is a pendant edge, right? These are our pendant edges. Why? Because it is an incident with the pendant vertex. If I am not considering this edge, so will it cover the graph? Here and all, you can, instead of taking this edge, you can take this edge also. Okay. So it will also cover the graph. But if I am discarding this edge, will it cover the graph? No. Also here also it has to be taken. Here I have taken different edges for this covering. But this edge is common in both the cases. So if you have a pendant edge, then it should be included in every covering of the graph. Every covering contains a minimal covering. if I can contain make any covering of the graph. There also I can add some more. If I am adding this also, doesn't matter. But this for the graph minimal covering I have put like this. Okay, so every covering contains a minimal covering. If we are taking a set of edges small g, and we will see what is the condition of the remaining set of edges. If the remaining edges are denoted by g minus g, the set of edges g is a covering if and only for every vertex v, the degree of vertex v in g minus g is less than or equal to degree of vertex v in g minus 1. Why? It is what we are saying that it is a covering. So that every vertex should be of degree. That if we are taking a vertex v in the main graph, and if it is the degree of that v in g minus g, that is we are discarding those edges that we are considering, and that those set of edges are said to be a covering if and only if that degree of vertex v in g minus g is less than or equal to degree of that vertex in the complete graph minus 1. Because what that g is a covering means it should be incident with every vertex in that g. Okay, so the g minus g, we are taking any vertex v in g minus g, degree of that vertex in g minus g will be less than or equal to degree of that vertex in the original graph minus 1. Okay, and now minimal covering can contain a circuit. Why? If we are having a circuit, we can easily remove one edge without leaving that vertex uncovered. So minimal covering of a graph of order n should not contain any circuit. And also, therefore, the minimal covering of a graph of order n can contain no more than n minus 1 edges. Like we know that a graph without circuit on n vertices have maximum n minus 1 edges. The condition is here. A graph in general has many minimal covering, and they may be of different size. We have seen in the last graph we have minimal coverings of size 6 and size 8. Both the coverings were minimal, because if we are removing any edge from that covering, the covering will not be minimal. So a graph may have several minimal coverings and may be of different sizes and consisting of different number of edges. And what is this? If a graph is containing a minimal covering, then what we call that? A number of edges in the minimal covering of the smallest size. It is called the covering number. That is, if a graph has different minimal coverings, suppose C1, C2, etc. And the minimal the covering with minimum cardinality is said to be a minimal covering of that graph. And that minimal covering is termed to be the covering number of a graph. Okay? Then minimal covering, then minimal covering and covering number. And usually this edge covering number is denoted by alpha 1 or alpha 1 of G. That is, we are specifying with respect to which graph we are describing this alpha 1. That is why we are calling this alpha 1 of G. Now we will see what is this. We have seen what is edge covering. Similar to edge covering, we have vertex covering. So first, therefore, edge covering, we have taken an edge, set of edges, and set of edges are set to cover G if the set of edges has an endpoint of every vertex belongs to as a endpoint of these edges. But now we will see what is vertex covering. Let G be a graph and C be a subset of the vertex set of G. And C is said to be a covering, that is vertex covering, if every edge has at least 119 C. We have seen that in edge covering, every vertex is at least 190 of those set of edges. Here we are saying that If C is a subset of vertices, then every edge has at least one ending this C. And this vertex covering with minimum cardinality is termed to be a minimum vertex covering. And that means there exists no other covering C dash such that cardinality of C dash is less than cardinality of C. That is minimum vertex covering. The number of elements in the minimum vertex covering is denoted by alpha naught, also known as the, or we can write like that, alpha naught of G. Okay, this is the vertex covering or covering number of G. Edge covering number of G is written as alpha 1 of G, and vertex covering number is denoted as alpha naught of G. Okay, now consider this graph. Graph with 11 vertices. Okay, then we can see the subset of vertices V1, V1, V3, V5, V6, V7, V8, V9, V10. If we are considering this subset of vertices, we can see that all the edges are incident with all these vertices, right? If we are taking this V1, V3, it covers all these vertices, this portion, and this V3 also, from here also this edge is incident with this, and V5, V6, all these vertices are being covered. All these edges are being covered, and here also all these edges are being covered. So it is a covering, vertex covering. Similarly, this also we have taken instead of changing the vertices, whatever it may be, V2, V3, V5, V6, V7, V8, and in V9, V11. That also is a covering of this graph. But is it a minimal covering? No. Because if we are taking this V4 itself, if we are taking this vertex V4, it will be a covering for all these edges, right? So V4 I am taking, and from here I am taking this V1. So does this V4 and V1 cover all these edges? No. So I have to take at least one more thing, V2 or V3. Similarly, if I am taking this V11, I have to take some more V9 or V10. So I have taken two different minimal vertex coverings of this graph. Okay. And so what is the minimum covering number? The minimal vertex covering. That is, covering number of this graph is, alpha naught of this is 5. Okay. So now consider the complete graph P with P vertices, KP. Complete graph. What is complete graph? The graph is said to be complete if every pair of there exists an edge between every pair of distinct vertices. So this complete graph. So for complete graph, the vertex covering number is P minus 1, and edge covering number is the integral modulo P plus 1 by 2. Okay. Now we will see this covering, edge covering and vertex covering is okay. I hope it's okay for you. Now we will see what is the independence number. That is, two sets, we say that if they are not adjacent, they used to be, some edges are said to be independent if they are non-adjacent. Similarly, two vertices are said to be independent if they are non-adjacent. Now we will be seeing the formal definition and let G be a graph and S be a subset of vertex set of G. That is, S is a collection of S is a set of vertices of G. Then S is said to be independent if no two vertices are adjacent in G. No two vertices of S are adjacent in G. I think this terminology is something sounding to some other terms that we have learned. It turns to the bipartite graph, bipartition and all. In one set of vertices, we say that they are non-adjacent. In a partition, we say that set of vertices in one partite set is non-adjacent, or they can be said to be independent. Okay, an independent set with maximum is said to be maximum if there exists no other independent set S dash such that cardinality of S dash is greater than cardinality of this S. The number of elements that means number of vertices in the maximum independence set is called the vertex independence number of G. Usually we call it as independence number of G, and it is denoted by beta naught, or sometimes to specify that it is with respect to a particular graph G, we'll be denoting like this beta. When considering some other graphs G1, G2, etc., for specifying the independence number, vertex independence number of us, which graph we are considering, we will be putting like this beta naught of G. So the maximum independent number, independence number is the number of elements in the maximum independence set, and that is called this independence number. Similarly, this what is called edge independence number. A set of edges are said to be independent if none of them are adjacent, and the maximum cardinality of edge independence set is defined as edge independence number, and it is denoted by beta 1, and it is for beta 1 of G. As here also we know that the complete graph with the vertices beta naught of Kp complete graph is 1. Why? Because why? If we are taking any vertices, it is adjacent to all other vertices. So here we can take beta naught of Kp to be 1 only, and beta 1 of Kp is p by 2, integer modulo p by 2. And now consider this graph. This one, here this alpha naught. What is alpha naught? Vertex covering number. And alpha 1, edge covering number. That is vertex covering number is here, it is 5. How we can take it to be 5? If I am taking every vertices, this how many vertices here we have? 1, 2, 3, 4, 5, 6, 7. 7 vertices cover the complete graph. So we are taking the minimum number of vertices required to cover the graph. That is minimum number of vertices that so that every edge has at least one end to be there. What is this 5? How I can take this alpha naught to be 5? How? If I am considering this vertex, suppose if I am considering this vertex, okay, then I can cover these edges. Can I cover any more edge here from here? No. So if I can take this also, right? So it will cover this edge and this edge. So next, which vertex I have to take? Is it required to take this one? No, better I can take this one, right? So it will be, this edge will be covered, and these 3 edges will be covered. So next, which I have to take? If I am preferring this one, these 2 edges will be covered. But will this edge be covered? So I have to take either this or this. So what is the cardinality of minimum number of vertices required to cover? So suppose I'm taking this edge, this vertex. So what is the minimum number of cardinality to cover? Minimum cardinality of vertices to cover this edge is 5. Okay. And similarly, what is alpha 1? Minimum number of edges required to cover the complete graph, right? And this alpha 1, how many edges that I require to cover the complete graph? So if I am taking this complete set of edges, how many I have to take here? I have to take only 4. Which all I am going to take? Which all I have to take? Suppose this one. Okay, so which all vertices will be covered from here? Only this vertex will be covered, right? So which all other edges which I can take? This and this will be covered. So which other vertices I can take? Sorry, which other edges I can take to cover other edges? So I have to take this also. So this all edges will be covered. Then which all edges I have to take? If I am taking this one, I can cover this. and to cover this vertex, I have to take at least one more edge from here. You can take either this, which one? So how many edges are required to cover the complete graph? 4 edges are required to complete the four edges are required to cover this complete graph. So alpha 1 is 4. Similarly, beta 2, which is the independent maximal number of independent sets. In maximum number of independent vertices. Suppose if I am taking this vertex, it is adjacent to 1, 2, 3. So we cannot take any of this. So then I am taking this one. So can I take anything else? No. So this beta 0 is 2. If I am taking this also, it's okay. When it is adjacent to all these 4 and this, I can take anything like this here or here, whatever it may be. It may be beta 0 equal to 2. And similarly, beta 1 equal to 3. So, for any trivial graph, we can find that alpha 0 plus beta 0 equal to P, the number of vertices of the given graph, which is equal to alpha 1 plus beta 1. And we see that alpha 1 plus beta 1, 7, which is equal to 5 plus 2, 7. Okay. That is the relation between the minimum vertex covering, edge covering, maximal independence number, vertex independence number and edge independence number. Now we will go to next question. The applications of edge covering. Suppose this is a street map of a city and each vertex is a potential troubleshoot. And suppose that what must be kept under not only this camera surveillance, it should be kept under some patrol car surveillance. How many minimum number of patrol cars has to be used to cover all these trouble spots? That is that we are asked to find. We have to find some patrol car surveillance such that we have to cover all these trouble spots. So if I am taking this route, they can cover only these 2 trouble spots, right? Like that. What is the minimum number of that the question reduces to like this. Smallest minimal edge covering. So if I am taking this vertex, if I am taking this edge, I can cover these 2 vertices. Similarly, if I am taking this edge, I can cover these 2 vertices. If this is taken, these 2 vertices. So all the 11 vertices can be covered with these 6 edges. So we have already seen that in edge covering, the minimum number of edge covering is, if any g is of order n, then it will be the integer modulo n by 2. The least integer modulo n by 2. Here it is also 11 and n by 2 means 5 point something. So we have to take at least 6. At least 6 petrol car surveillance is required to cover the trouble spots in this case. Okay. Another thing is this dimer problem. What is this dimer problem? In crystal physics, the crystals are represented as 3-dimensional lattices. While each vertex is a lattice, each vertex in the lattice represents an atom, and the edge between the lattice vertices represents the bond between 2 atoms. On the study of the surface properties of crystals, it is represented by means of 2-dimensional lattices. To obtain this certain analytic expression containing certain properties of these crystals, that is containing that diatomic molecules called dimers, it is required to find in which way all these atoms of this 2-dimensional lattice can be paired off as molecules, that is consisting of 2 atoms. The problem which is that we have to find the relation between these 2 vertices, that is 2 different atoms, and how they are related. So that is problem of edge covering of given graph, such that every vertex in the covering is of degree 1, and such that that means independent edge covering. We'll see what other things in the next sessions like factorization and all. It's what called on-factor. Such a covering in which every vertex of degree 1 is called a dimer or on-factor. A dimer covering or an on-factor. A dimer covering is obviously matching because we have to find that every vertex is of degree 1. That means no two edges are adjacent. So means it is a matching. What is the concept of matching? Subset of edges which no two are adjacent. So it is a matching. Moreover, dimer covering is a maximal matching also. Now consider this one. This will be the how the occurrence of this dimer coverings happen. And we can see that if it's all a matching, this borderlines are this dimer covering. And we see that if a dimer covering is possible in a graph, it should have even number of vertices. And results on some covering. An edge covering G of G is said to be minimal if and only if G contains no paths of length 3 or more. That is, a covering is minimal if it doesn't contain any paths of length 3 or more. What is this path? It is an alternating sequence of vertices and edges, starting and ending with vertex, and such that do any vertices repeat? No. Do any edges repeat? No. Here, suppose that G is a minimal covering and contains a path, does not contains any path of length 3 or more. Suppose if it contains a path 3 or more, that we can have like this, right? V1, E1, V2, E2, V3, E3, V4. It's a path of how much? 3. Here we are saying that does not contain a path 3 of length 3 or more. And I have taken a path of length 3. Suppose this edge E2 is removed from that path. Will our things, what is this covering condition mean? We have that every vertex should be at least one endpoint with that edge. If I am removing this edge E2, does it affect the covering of a graph? No, because even if this E2 is removed, this vertex V2 is adjacent with the E1 and V3 is adjacent with V3. So it doesn't affect it doesn't make the vertices V1, V2 and V3 uncovered. Therefore, the G that we consider was not a minimal covering. Hana, because we say that what is a minimal covering? Even if we take out an edge, it doesn't make the covering undisturbed. So there exists no covering, no minimal covering, such that it is no covering which is minimal. So we have taken that G we consider to be a minimal covering, but it is, even if we remove one edge, it is not affecting the covering property. So it was not minimal. So if we are taking a covering, if it is minimal, then it doesn't contain any path of length 3 or more. Okay. On the contrary, assume that G is not containing any path of length 3 or more. Or then it contains this. On the contrary, assume that the covering G is not containing any path of length 3 or more. All the components must be star graphs. Why? If it is minimal covering, then there were this 4y. From a star graph, no edge can be removed, leaving any vertex uncovered. Suppose if I am taking this edge from this star, then this vertex will be removed, will be made uncovered. So from graph, we cannot, from star graph, we cannot take any edge from that. So that G will be minimal. Okay. Suppose if I am taking any edge from this star, then this vertex will not be covered. That is why, so if it is path not containing path of length 3 or more, it must contain, the components must be star graphs. And this is the examples of star graphs with one edge, two edges, three edges and all. If I am taking any edge from any component, then some vertices will be left uncovered. So if G is a minimal covering, then the graph, it doesn't contain any path of length 3 or more. Okay. Now some other results on this covering. Let G be C be a vertex covering of a given graph. If M is a matching of G, then this cardinality of matching will be always less than the vertex covering. And if M is a matching such that cardinality of M equal to cardinality of the vertex covering, then M is maximal matching and C is the minimum covering of G. Actually, this equality doesn't hold for generally. This equality doesn't hold for a general graph. We'll see. Here, what is M? From the definition of M, we can see that M is a set of edges which are not non-adjacent. So here, if I am taking this edge, can I take any of these edges? No. So I can take this edge. So if I am taking this edge, can I take any of these edges? No. Then from here, I can take one more edge. So the cardinality of this M is equal to 3. I hope you are familiar with the definition of matching. And so the cardinality of M equal to 3. And also from here, we have already seen that this vertex covering is 5. So this for in general cases, this M is the maximal matching and C is the minimum vertex covering. Here we have seen that in some cases, if M matching such that cardinality of M equal to this cardinality of M equal to cardinality of C, then M is maximal matching and C is minimum covering. So in general graphs, it is not possible. So it happens only with this some particular kind of graphs. We will see those results. And these results have been given by the mathematician Koenig. And this here we can see that how it is. Let G be a bipartite graph. The number of edges in the maximal matching is equal to the number of vertices in the minimum covering of graph. So Koenig has proved that maximal matching and minimal covering occurs in the cases of bipartite graphs. Consider this graph. This graph given by Koenig. This is a bipartite graph with 14 vertices. Upside also there are 7 vertices and down also there are 7 vertices. This one partition, if it is a partition named as U, it is U, and if it is a partition is named as V. Here we have 14 vertices. And if we are considering this bipartition as like this, where U1 is related to V2 and U6, V6. Similarly, every partition is shown like that. And from here, we can see that if these board lines are considered to be the matchings. I hope it is okay. Are they adjacent? Anyone are they adjacent? No. And this covering bold vertices with mark in bold. This one, this one, this one. Okay. These 6 vertices. Do these 6 vertices cover all the graph? Yeah. This, if you are considering this, these edges are considered and all this. Just take on little bit attention onto the figure and see whether these vertices and edges. So it is maximal matching and minimum vertex covering. This happens here. It's due to the Koenig. Okay. Now we'll see what is the interpretation of Koenig's theorem. It involves 0-1 matrices in which the matrices whose entries are 0-1. It states like that: A be a 0-1 matrix. That is, the entries of the matrix A is either 0 or 1. Then the maximum number of 1s in matrix let A be a 0-1 matrix. Then the maximum number of 1s in matrix A, such that no 2 1s of which lie in same row or column, is equal to the number of 1s, number of rows and columns of A. Together that contains all the 1s. What does it say? Let A be a 0-1 matrix. Then the maximum number of ones in A, such that no two ones lies in the same row or columns. That is, the number of ones, independent number of ones in the rows or columns will be equal to maximum is equal to the minimum number of rows, that the rows and columns together, the rows and columns which the maximum contains all the ones. Let's see. Suppose we have a graph that Conic has proved for a bipartite graph, right? Cardinality of M equal to cardinality of C, maximal matching equal to minimum vertex covering. That has been done with part of this bipartite graphs. So here also we are considering this bipartite graphs. Let G be a bipartite graph with vertex at V1 and V2, with cardinalities N1 and N2. And let A be a matrix like that, A N1 by N2. This and such that Aij equal to Aij, the elements of N1 by N2 is represented by A equal to 1 if Ui is adjacent to Bj, and 0 if not. We'll see with an example. Then the matching corresponds to the collection of ones. No two of lies in the same row or column, and covering corresponds to the collection of vertices of G that corresponds to rows and columns of A together contain all the vertices. Let's see, consider this graph. We have this graph with vertices V1 and V2, and the elements are named as A to E and A to F, small a to F. So I can write this by adjacency matrix of this graph is defined like that. Hannah? That I think I have already told you. It is 0, A N1 by N2 and A N1 by N2, the transpose of that matrix, and 0. So here we have N1 equal to 5 and N2 equal to 6. So total number of vertices 11. So I have this graph 5 by 6 matrix. So sorry, I have this matrix A N1 by N2 equal to 5 by 6 matrix. Like this, I have just marked. So I have these entries. First one, if it is A, B, C, D, E. If it is A, B, C, D, E, F. Here, this A is adjacent to B and F. That is why this conditions like that. Okay, A is adjacent to B and F. So similarly, B is adjacent only to B. Now the matching matrix is like this. We have already seen the some procedure to how to find the matching matrix. We have find this taking this first row containing only one element, one entry. Then we took and deleted this first, then deleted this column. Then in my previous session of matching, I have discussed in detail this how to find the matching matrix. So on finding this matching matrix, it is like that. So how many number of only one are there, neither in rows or column we have, it is 5. Similarly, if we are taking is as in a combination, what is the total maximum number of vertices and edges, number of rows and columns with a maximum edges is here also is 5. Now we'll see in detail. The matching corresponds to this 5, AF, BB, CE, DD and EF, and the covering corresponds to this A, B, C, D, A, this one, A, B, C, D and this E. This not this B, this B, B, C and D. Okay. A, B, C, this A, B, C, E and D. And now before going to the next session, we will see what is this critical vertices and edges. If we know that if H is a subgraph of a given graph, then alpha naught of H which will be less than or equal to alpha naught of G. This in particular, this holds when h equal to g minus v or h equal to g minus c. So if alpha for every vertex v and e, if alpha naught of g minus v is less than or equal to alpha naught of g, then v is called this critical vertex. Similarly, if alpha 1 of g minus e is less than alpha 1 of g, then e is called the critical edge. That is, removal of that mean reduces the removal of a particular vertex or particular edge, decreases this covering number, then that edge or vertex is termed to be a critical edge or critical vertex. A graph is said to be vertex critical if all the vertices are critical. And graph is said to be edge critical if all the edges are critical. So if the removal of the edge E which is incident with the edge vertices u and v decreases the covering number, then the removal of u or v must also result in a graph with smaller vertex covering number. Thus, on remark is this important remark. Thus, if edge critical, surely it will be vertex critical also. Meanwhile, the graph which is vertex critical need not be edge critical. That is, for example, C4. All the vertices of C4 are critical, because even if we remove any vertex from C4, this vertex covering number will be reduced. But it is not edge critical, because even if we remove any edge from that, the covering number is not going to be reduced. And characterization of critical vertices. A vertex V in a graph G is critical if and only if some minimum covering contains this vertex V. That is, if V is contained in some vertex minimum covering, then only it is said to be a critical vertex. Why? The removal then from minimum covering, if we are removing that vertex, it will be disturbing the covering number. So it must be contained in some vertex covering of G. So we have discussed what is covering of a graph, what is covering, that means it is incident with. That is, covering means simply means it is incident with that relation only. And what is vertex covering and edge covering? Set of vertices is said to cover a graph if all the edges are incident with those vertices. At least if every edge has at least one end as this set of vertices, and similarly the edge covering. And what is covering number? Minimum number of vertices required to cover the graph, or minimum number of edges required to cover the graph is called covering number. And is independent set, the set of edges which are non-adjacent. And that set of edges and set of vertices which are non-adjacent, that also independent set. Then we have seen the independence number, maximal number of edge independent set and maximum number of vertex independent set is termed as independence number. And we have seen what is conics theorem. And we have seen the critical vertices and critical edges. I hope you enjoyed this session. Thank you for watching. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.